we were talking about this question. I just changed few values in this question. Okay, so because this previously it was like not 11 males, it was like 30 males and sorry 31 males and 31 female. So I just changed it to 11. Okay, because there is a reason. I think did I? Okay, sorry I haven't mentioned it, but consider, okay, consider this is I mean the populations are normal distributed. Okay, just consider the populations are normal distributed. I think I forgot to mention that. Okay, that's fine. Right, this is study based on genders, 11 male 11 females, based on their error on directions. Okay, average error on directions. Okay, 11 males. There are two populations, male population and female population. From those two populations, we have taken two samples. Let me call this N1. We call this N2. Okay, these are the sizes of two samples. They are independent, so don't worry about that. They are independent at 10% significant level. So we know what is alpha, 0.1. So what we are talking about, hypothesis testing or confidence intervals. Hypothesis testing. Okay, right. What is the claim? Data provide. Okay, this is the claim. The data provides evidence to conclude that on average make have low error on direction. So I told you last day, this is our keyword, low, which means less than. X bar, x1 bar given, x2 bar given, s1, s2 they are given. Okay, so first thing is let's use critical value approach first. So first thing is define your mu1 and mu2, because you know that H0 or your null hypothesis based on this, always mu1 equals mu2, or simply you can write it like this, H0 mu1 minus mu2, whatever, doesn't matter, they are same. Okay, and also alternative hypothesis you can write based on our the keyword low, mu1 less than mu2. So how did I decide what is this mu1 and mu2? These are mu1 mean population mean error of male, mu2 is population mean, so mu mean normally population mean of what? Error of female. Okay, clear? See, error direction on female and error direction on male. That's what we are comparing here. So x1 x2 values given. So this is your mu1 and mu2. Let me erase this. So mu1 and mu2 versus, sorry, not mu1 and mu2, H0 and H8. This one versus this one. Okay, right. So next one is next step is finding alpha. Alpha is 0.1 because it is 10%. Okay, because it is about 10%. So next step, which is calculating the pooled standard deviation, SP. Okay, SP. Why do we need this? Because if you remember, our goal is to calculate the test statistic. So that test statistic T is what? X bar, sorry, x1 bar minus x2 bar based on under H0. Okay, under H0. Let me note it here, under H0. Under H0, we don't have mu1 minus mu2 because it is 0. Okay, this divide by SP times 1 over n1 plus 1 over n2. I think yes, this one. Okay, we don't know this guy, SP, pooled sample, pooled standard deviation. To find that, we can use this giant equation. I told you this this denominator, it is degrees of freedom of those samples. Okay, once you plug the values, you will see n equals 1. Sorry, n1 is 1, n2 is 1. Okay, so the value is 43.68. Okay, this is SP value. So you can simply plug this value to this equation. I Yes, this is the test statistic. So plug this value right here. X1 and X2, sorry, X1 bar and X2 bar given from last slide. So this calculation gives you negative value, negative 0.1767. Okay, I think calculations are correct. I checked them. So this is your test statistic. So now what? Next step is find the critical value. Okay, find the critical value. So how do we find that? Based on our alpha, right? Based on our alpha, see, this is a one tail test. Which one? Left tail. Okay, this is a left tail test. Okay, which means it's gonna be like this. Okay, so definitely this t value, table t value is negative. Definitely it's gonna be like one tail. So this alpha, negative t alpha, comma, is degree of freedom. This value is right here. So degree of freedom is 20, n1 plus n2 minus 2. It is sorry, this is 20. I didn't see that. Okay, it is 20. I think this value is correct. I believe that it is correct. For based on t 0.1, this is your alpha, this is your df, degrees of freedom. The value is, stable value is negative 1.325. So what is your test statistic value? Negative 0.1767. Value 1. Negative 0.1767, right? So this is your test statistic value, or t, somewhere here. Clear? Because t alpha, sorry, not t alpha, this value less than your t value or t cal, whatever, calculated t value. This is negative 1.3 something, but this is negative 0 point, right? Yes, negative 0 point. So negative 1.3 somewhere here, negative 0.1 somewhere here. So it is outside the rejection region. Okay, so see, something like this. You can simply forget about this part. Yes, if value is not there, I mean degrees of freedom value is not there, you can simply approximate it, but here you don't need it. Okay, please do the corrections, because in your note the values are different. Okay, I think values are 31. So based on that, we have some calculations. I change it. Okay, I'll upload, I think not today, maybe tomorrow I'll upload the correct notes based on this. Okay, so this is your t alpha negative. So this is your negative t alpha df. This is your t cal, or t value, test statistic value. Based on this, you can take your decision. Sorry, see, this is greater than this one, which means outside the rejection region. So we do not reject H0. Okay, we do not reject H0. So finally, you can give your interpretation. 10% significant level, we do not reject. Sorry, we do not have enough evidence to say that they are clear. Okay, clear? Again, I just change the example, not the example, values. Next, let me go through a p-value approach real quick. First few steps, they are pretty similar, this versus this, right? Alpha same. So third and step up to step 4, pretty similar, everything is similar. So you can see this is your t cal. So now based on this test statistic value, you have to find the corresponding alpha value. Okay, so let's do this. Here degrees of freedom 20, yes. So using this is a left tail test. So where is that? Okay, so once I found the p value is somewhere greater than 0.1, greater than 0.1. Okay, p value, what's the p value? P value based on your test statistic value. It is your t cal negative 0.1767, something like that. Okay, so degrees of freedom is 20. Go to the C table, go to the T table. First find where is degree of freedom 20. Okay, then try to find the, it's not about negative, there are no negative values, so don't worry about that. Then try to find the 0.1767. Okay, that's how we deal with this. I don't think you can find the exact value, but you can approximate. Okay, when you are approximating, don't forget, as I mentioned, always try to find what happened if you are starting from left, if you are going left to right. What will happen to the alpha values? Alpha values are decreasing or increasing, and T values are decreasing or increasing. Try to understand that pattern, and you can approximate this value. Okay, so this is your P value, this is your test statistic value. Basically this P value greater than 0.1. What is the 0.1? It is alpha. Okay, so once you calculate, you will see that your P value is greater than 0.1, which means we do not reject H naught, right? I mean, at what time we reject H naught? If P value less than or equal alpha, then we reject H naught, right? This is the criteria. Reject H naught. Otherwise, we do not. Otherwise, do not reject H naught. Okay. So we have otherwise situation. We don't need to reject our H naught. Okay. So same conclusion, same result using P value or critical value approach. Right. Now we are moving to confidence interval. Okay, it is we don't need to talk too much. Okay, so but I just need to give you a brief idea before we about how do we calculate confidence intervals based on this population two population situation. Assumptions are pretty similar what we have used. So confidence intervals, since you know what's the confidence interval, I don't need to explain it again. I can simply give you the formula to calculate the confidence interval. Okay, this one right here, definitely you can find using your problem. Okay, they have given, or you can calculate that. T alpha over 2. Okay, always remember this one. When you are going to calculate confidence intervals, it's going to be definitely alpha over 2. Okay, T alpha over 2. And you don't forget your degrees of freedom. SP, you have to calculate. It's a pool standard deviation using that giant formula. Okay, then this one. So this is the formula. Just try to remember this formula or try to use this formula. Other than that, everything are pretty similar what we have done. So in this problem, I mean, let me use the previous problem for this case. 90% confidence interval, which means our alpha is 10%, as we mentioned last time. So that based on that, alpha over 2 is 0.05. Okay, so first go to the T table and find this value, T alpha over 2 comma degrees of freedom. Degrees of freedom, it is 20, right? Using the T table, you can find that value is 1.725. Okay, next plug those values here. X1 bar you can find from the question, this from the example, same example. This is the T alpha, this is yes, T alpha over 2 comma degrees of freedom. This is your SP, pool sample, pooled standard deviation. Okay, this is N1 and this is N2. That's it. Okay. Do some math, just simplify this a little bit. You will get 90% confidence interval mean error differences between male and female. It is this. This is your CI, 90% CI. Okay. Once you simplify this, you will get this result. Okay. I don't think I need to do more examples based on this because you know how to calculate this. You just need to know this one, this formula. Okay, so this is what you need. This formula here, T alpha comma degrees of freedom. Okay, you just need this formula to calculate the confidence interval. Okay, any questions? Okay, let me move to the next, the last section of this course. 10.3. Okay, what we were talking about last, sorry, what we were talking about in section 10.2, it is about this. We don't know their standard population standard deviations, but we know one thing, which is they are equal, but we don't know. Okay, so that we use what? We use pooled standard deviation to replace sigma and deal with pooled t-test. Okay, in this section, it's kind of an extension. Situation is a little bit different. Now standard deviations are not equal, and also we don't know the value of the standard deviation. So sigma, no, it's not sigma. Sigma 1 and sigma 2 unknown. They are unknown. We don't know them. And at the same time, they are not equal. They are not equal. Okay, that's the situation. So we have to do the same things for this situation. According to this scenario, we have to find the hypothesis testing and confidence intervals. Okay. So let me recall this one. How to calculate the test statistic for x1 bar and x2 bar. Okay. So test statistic is this one: z equals x bar differences minus mu differences divided by square root of their standard deviations, not the standard deviation, variances divided by their individual sample sizes. This is variance. Okay, remember, variance. Variance equal, which means variance means standard deviation square. Okay, right. What happened? Okay, since sigma 1 and sigma 2 are unknown and also they are not equal, so we have to estimate them using sample standard deviations, something we did in early chapters, chapter 6, maybe 7. So thing is, you can simply replace. So here we replace sigma 1 and sigma 2 using S1 and S2 respectively. Okay, that's the only thing we need to do. But once we replace S1 and S2, we should know how to find them. Okay, same test statistic, it doesn't change. Only difference is here we don't have SP or sigma, we have S1 and S2. They are different. So S1 not equal S2. Okay. Again, we have to use the T distribution. Since we know, since we don't know sigma, we have to use the T distribution. So how do we find the degrees of freedom? Again, it is not simple as previous case. It is not n1 plus n2 minus 2. So in this case, we cannot find df using n1 plus n2 minus 2. So we cannot find the degrees of freedom using that. Instead, we have a giant formula again, okay, to find the degrees of freedom. The first part, the numerator, It is the squared version of this denominator part, and yes, it is huge. I know that it is huge, but all values you know, S1, you know S2, N1, N2. There are only 1, 2, 3, 4, 4 different values. Okay, this giant formula based on 4 different values. All 4 values definitely you know. Okay, I mean when if you are dealing with these questions, you know that. Okay, the thing is, once you perform this calculation or once you do this calculation, you will definitely get a decimal number. Okay, definitely you will get a decimal number, so that you have to round down that number to the nearest integer. For example, if you get a value like 9.53, okay, always round this down, consider it's 9, because why we are rounded down, because we are dealing with sorry, our goal is to find the degrees of freedom, not the sample size. Okay, that's why we are rounded down. Okay, it's not about samples, it's about degrees of freedom. Okay, that's why we are rounded down to the nearest integer. So I think I don't need to explain what is this. This is just a giant formula. You don't have to remember this. Okay, you have I call that formula sheet. You can find this. Okay, so you don't need to remember this one, but you should know how to calculate this. Okay, just plug the values and calculate this. As always, use your calculator. Okay, right. So I think yes, that's the only difference in this section. Okay, you replaced S1 and S2 instead of sigma or SP, and also degrees of freedom you have something else, not N1 plus N2 minus 2. It is different. Okay, so please don't forget this one. Okay, you cannot use this guy for this specific problem, which means if you don't know sigma 1 and sigma 2 at the same time, they are not equal. Okay, right. So all negative and null, always all negative hypothesis, mu1 equals mu2. Null can be 3 cases. Sorry, all negative hypothesis can be 3 cases, always null, mu1 equals mu2. Based on your alternative hypothesis, it can be a not equal, greater than, or less than case. One tail or two tail. So test statistic again, this one is your test statistic under H0. That's why we don't have mu1 minus mu2. Under H0, mu1 minus mu2, it is 0. Okay. So yes, we have to use the T table. Degrees of freedom. The next step, definitely you have to calculate the degrees of freedom. Okay, degrees of freedom using this, and final answer, round it down. Let's check how we use the critical value approach. So yes, all 4 steps, I think they are pretty similar. State the null, alpha, find the significant level, and then compute the test statistic. Now you don't need pool, you do not need SP. Okay, we are not talking about SP. You need S1 and S2. S1 and S2. So you can definitely calculate that, or you can find it from your problem. Find the critical value. Okay, then find the critical value using T table. Okay, which means T alpha comma your degrees of freedom. This degrees of freedom, how do you find? Using that giant formula. Okay, using giant formula. If it is a left tail, again the same 3 stories. If it is a left tail, alpha value T alpha value definitely negative. So if T alpha, negative T alpha greater than your T value, then yes, you have to reject your null. If it's a right tail test, your T alpha less than your T value or test statistic value, you have to reject. If you have two tail test, either this side or this side, T greater than T alpha over 2 or T less than negative T alpha over 2, negative part here, positive part here, then you have to reject your null. Okay. Based on p-value approach, steps are pretty similar up to calculate the test statistic. Go to the t table and find the p-value. So based on all cases, your p-value, you reject S naught if your p-value less than alpha. That's the one and only condition. Okay. So how do we find this value? This is delta. So your p-value equals delta. If it is a right tail test, delta is this. So your p-value is 1 minus delta. What is delta? The t test. I mean the area that you can find according to the test statistic value. Okay, using t table. Okay, and also this is delta. This is delta. So your not 8 delta. So your p-value is 2 times delta. Okay, clear? Okay, let me check. Okay, we have example. I think this is the first example, right? Okay, I know this this chapter 10 is it's like came from nowhere, something like that. No relationship. It's like don't know. Still, we were talking about. I mean, up to chapter 11, we were talking about one population or one mean. But here suddenly we have two population. Okay. The idea behind this, we just need to give you a brief overview about how we deal with two populations. But believe me, when you are dealing with two populations, it is the situation is very complicated than you think. Okay, so this is just an overview. That's why I told you I'm not going to give you many questions from this chapter, maybe one. Okay, right. So this example based on several neurosurgeons wanted to determine that following the table 5. Okay, at 5% significant level, 5% alpha, 5%, which means 0.05. So our claim is, so their claim is this one. Do the data provide sufficient evidence to conclude that the mean operative time is less? Since it is less, this is a right, left tail test. Left tail test. Okay, so this is a left tail test. They have mentioned assume both populations are normal distributed. So x1, let's consider x1 dynamic group and x2 about static group. Okay, so this is about mean operative time is less than with the dynamic system, less with the dynamic system than with the static systems. Okay, so dynamic less than static, right? So n1, n2, s1, s2, x1 bar, x2 bar, all values are given. All values are given, and yes, sample sizes are less than 30, definitely. See, these are the values. So you have the value set. Let's use the critical value approach. Step 1, define your mu1 and mu1 and mu2. Mu1 based on the dynamic group. So population mean of operative time of this dynamic group. Mu2 is same thing for static group. Then define your, so state your state H0 and HA. That's what they have done here. This versus this. H0 always mu1 equals mu2. Since this is a left tail test, it is a less than. Okay. Now step 2 is find the alpha. Alpha is 0.05. Calculate the test statistic. Under H naught, always you calculate the test statistic under H naught. Okay. So that mu1 minus mu2 equals 0. That's why you don't have mu1 minus mu2. Okay. Calculate this, then you can get your t cal value or let's say t test statistic value. Okay. I believe these values are correct. Let me check again. Next one. I don't think x1. Yeah. X1 is 300 something. X2 is 400 something. Yes. Values are correct. Okay, values are correct. Next step is find the degrees of freedom. Check this one. This is the formula for the degrees of freedom. How to find the degrees of freedom. And once you plug the values, it's going to be like this. In denominator, S1 squared over N1 squared. That squared term doesn't belong to this N1 minus 1. Okay. So please don't consider it as like this. It is not like this. Okay. So please be careful when you are plugging the values. Okay. Right. So once you calculate, you will get this degrees of freedom 17.82. As I mentioned, round it down. Always round down 70. Okay. So your DF or degrees of freedom is for this problem is 17. Okay. Now you have 17 degrees of freedom. Go to the T table and find your critical value. T0 T alpha comma DF, which means alpha is 0.05, DF is 17. Based on that, you can find your T values 1.74. Okay. Since this is a left tail test, you have to consider that value is as negative. Okay, negative T alpha. Step 5 is this is your T alpha over 2, sorry, T alpha comma degrees of freedom, and this is your T cal or test statistic value. So according to this figure or this picture, you can see your T cal value less than, or simply I call it T value, T value less than your T 0.05 comma DF. DF is 70. Okay, which means inside the rejection region. Inside the rejection region. So reject H naught at this 5% significant level. Okay. In chapter, sorry, not chapter, homework 10. Have you tried homework 10? Started yet? Yes. So did you find any different questions? I mean, difficult questions in chapter not 11, 10? Something like how do we understand? How do we differentiate that this is based on section 10.2 or 10.3, which means have they mentioned anything about standard deviations? Standard deviations are same, but they are unknown. Have they mentioned something like that? Have they mentioned the question? Okay. Most of the time, I mean, not the homework questions, it is really hard to identify. Okay, it's really hard to identify this based on sigma. Yes, sigma 1 and sigma 2 unknown, but they are equal or not. Most of the time, they haven't mentioned whether they are equal or not. Right? That part sometimes is missing. So at that point, questions can be a little bit tricky. Okay, questions can be a little bit tricky. But since you mentioned you don't, I mean, you didn't see any questions like that in your homework, I don't think that can pop up in a final exam. If, I mean, we don't need to put you guys in on a trouble, so we always try to give like if okay, like this, if you have question from this section, not this section, sorry, this chapter, definitely you will see that okay, sigma 1 and sigma 2, they are different, or like they are equal, something like that. We don't know sigma 1 and sigma 2, but they are same, they are similar, they are equal. Or we don't know sigma 1 and sigma 2, but at the same time they are different, something like that. Okay, using that keywords, you can differentiate these two. Okay, clear? So if, remember this one, if sigma 1 and sigma 2 unknown, and at the same time sigma 1 equals sigma 2, then you have to use what we did in section 10.2, section 10.2. okay, if sigma 1 and sigma 2 unknown and they are not equal, then you can use section 10.3. okay, 10.3. actually there is another section 10.4, but I believe that we don't need to go over 10.4. I'm not sure whether we have homework questions from 10.4. Has anyone done done homework 10? Did you see any questions from did you see anything that we cannot do based on these three sections? No. Yes, definitely. Then I have removed that because I don't remember. It's a long time ago, I don't remember. There is another section 10.4, but I think we don't need that. Okay, sorry. Yeah, 10. You yes, you have only 10 homeworks. Okay, as I mentioned for last week of this semester, you can go over all homeworks. Okay, so please make sure that you have completed all the homeworks before the last day of the class, so that you can get those 15 points. Okay, clear? Okay, right. So last part, this is the very last part. I think there are 1 or 2 slides, so I'll go over this a little bit faster. Confidence interval. So same as previous case, we can find the confidence interval, but when you are going to deal with confidence interval, you need this T alpha over 2 with degrees of freedom using, how do you find that? Using that giant formula. Okay, using that giant formula. And also you have to replace sigma 1 and sigma 2 using S1 and S2. That's the difference. Okay. I don't think we have example, but yes, we can use the same example what we did in this section. Alpha, I think it was 0.1. Yes, so we use 0.05. This is alpha over 2. Yes, degrees of freedom, you found it. It was 17. So T alpha over 2 comma 17. You can go to the table and find this value. Here you don't need to worry about negative or positive because we are dealing with confidence interval. That positive and negative, this one take care of that negative or positive. So you don't have to worry about that. Okay. Plug the values. This one x1 bar. This is x2 bar. This value based on your T 0.05 comma 17. S1 squared. S2 squared. N1. This is N2. So final value is this one. This is your interval. 90% confidence interval for these two is this, from this to this. Okay, clear? Okay, I think yes. So that's all about chapters. Oh, and also that's all about lectures. Okay. Next day on Monday, there is another note I have based on this chapter 10. I'll go over that because there are a few problems in that note, so that next Monday I can go over problems based on chapter 10, maybe chapter 11 if I have enough time.